In this video, we present our paper, PATS, Patch Area Transportation with Subdivision for Local Feature Matching. Here, PATS shows strong robustness in large-scale differences. It always maintains much higher number of feature matches and higher coverage rate in the image pairs. To achieve such an effect, our greatest contribution is modifying the traditional point-based one-to-one matching to a many-to-many matching between patches with area attributes. Now, the basic units for feature matching are no longer symmetrical. Feature matching aims at establishing sparse correspondences between a pair of images, which provides a solid foundation for various application scenarios, such as simultaneous locating and mapping, SLAM, and augmented reality, AR. This figure is cited from ColMap, a well-known work of SFM, which shows that more features are matched and more evenly they are distributed over the whole image, the higher the score. ColMap considers them the most important issue in feature matching besides the accuracy of the feature coordinates. They are also the goals of our work. In the following, we will introduce the three popular feature matching frameworks and explain the main drawbacks of them. Their names are detector-based method, detector-free method, and optical flow-based method. The detector-based framework is the most classical approach. This approach first obtains the feature map, then uses the detector to obtain feature points and feature vectors from it, and finally obtain the closest matches in the feature vector distance. The biggest problem is that the feature points are not evenly distributed, so it is easy to have feature point-free regions locally. The detector-free framework has recently become more popular than the detector-based one. The major difference between them is that detector-free framework extracts feature points from the image uniformly and can refine the coordinates of feature points jointly with information from both frames, so the matching error is also smaller. However, as shown in the figure, it encounters difficulties in large-scale differences and many-to-many matching problems, and tends to produce excessive errors in the rough matching stage, which are difficult to pull back by the subsequent refinement matching stage, so they will lose many matches and decrease the coverage. Some optical flow methods also try to solve feature matching problem. The steps of this method are exactly the reverse of detector-based, where optical flow matches are first generated, and then detector extracts feature points to choose which matches to use as feature matches. This framework can avoid the difficulty of many-to-many matching. However, optical flow often lacks the robustness as feature matching in the face of more complex scenes with larger viewpoint differences. Here we can see that none of three ideas mentioned before can solve the problems of point accuracy, robustness, and feature point coverage at the same time. The following image shows the different 3D reconstruction results with some popular matching method and ours. It has a clear representation of their problem. Lofter and Aspanformer, as detector-free methods, have excessive unmatched regions, while PDC Net Plus, as an optical flow-based method, has a relatively large matching error. And we are able to synthesize the three problems to come up with a more satisfactory answer. Our approach is closer to the detector-free framework because we also partition the image into many small patches of the same size. But here, what we find is not the matching coordinates of a point in the patch, but the matching relationship of the whole patch, which is many-to-many. And due to the difference in scale, we introduce an area property for each patches, which is determined by the relative amount of real objects in this patch, so the smaller the object appears to be, the larger its area property is. And considering that area is a relative attribute, we set the area attribute of all the patches on reference frame to 1. The subdivision is done to complete the coarse to fine step, where the patches on reference frame that previously completed the matching, along with their projection on the target frame, are extracted and resized to the same size at this step, and then used as input for the next iteration. This figure shows the results of the new images extracted from the reference frame and the target frame. We can easily find the similarity between these cropped images. This experiment proves that we can achieve amazing results on image pairs with large-scale difference. The coverage of our matches is higher than others, about 50%, and the precision of our matches is always a bit higher than others. More quantitative experiments can be found on our paper. Here are some of visualized results. PATS combines both accuracy and coverage, so that a 3D reconstruction with fair results can be done using only the matched feature points between two frames with large viewpoint changes. Here are our results. Thanks for your watching. If you are interested in our work, you can find more information on our project page.